So for the first problem, we have an equilateral triangle of charges. I'm going to kind of brush through the first few parts because this should be something that you can check on the simulator. I'll just re-explain the intuition for what's going on. So remember, electric field lines point away from positive charges and into negative charges because they show where a positive charge would go. And a positive charge is going to be pushed away from another positive charge, but pulled in to a negative charge, right? Opposites attract, like charges repel. And so here, this is what it'll look like broadly. Again, do it on the simulator to see what it actually looks like. But you can see that behavior is clear, right? A positive charge is going to be pushed away from here, but it's also not going to go towards this because it also wants to be pushed away from there. So it gets pushed and then deflected, and then this negative charge pulls it in. Okay. So remember, positive charges flow along the electric field lines, right? That's another answer to one of the questions. And high potential is going to be over here. High V. Low potential is going to be over here. Low V. Because high to low potential is the way that positive charges flow. And in circuit analysis, we always talk about the flow of positive charges in circuits because it makes our life easier. It's kind of just a choice. So, yeah. Now, the actual interesting parts of this question are parts 2 and 3. So first, I asked you to draw equipotential lines. What I mean by that is, suppose we had just a single charge, okay? Just a single positive charge. If I'm here versus if I'm there versus if I'm here, at any of those points, if I'm here versus if I'm here versus if I'm there, at any of those points, to me, all that matters is distance from the charge, okay? So the potential is different at these points, but along a circle around this point charge, here, 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 the potential is the same. This you can actually prove that using some of Maxwell's equations and some deeper things that we're not going to talk about. So there's a formula for electric potential. V equals K Q1 over R plus K Q2 over Q2 over R plus and so on for all the charges that you have. So in this system, we have 3 charges. We have a Q1, a Q2, and a Q3. K is just a constant. It's a number equal to 9 times 10 to the 9th power. And R is the distance from those charges at your point of space. So say I'm standing right here, R1, R2. If this is charge 1, then R1 is that distance, R2 is this distance, and R3 is this distance. This is Q1, this is Q2, this is Q3. Okay? We just add up all their individual contributions. And the reason why that is gets a little mathematically deeper, but it makes sense, right? Each charge is just acting like another spring that is pushing you away. So yes, they interact in how they push you away, but as an isolated unit, their pushing behavior is like what they would do if they were on their own is not changed when you put another charge over here. It's not going to change this charge kind of punch the other charges away, right? So if we were to calculate that for this configuration, we're in that right there, and we have a triangle, okay? Now you need to know some trigonometry for this, but this distance A, this distance A, this distance A. We're interested in what this distance is right here. Now, first of all, by symmetry, this is an equilateral triangle. So these 3 distances should all be the same because it's just a completely symmetric system. So let's call this distance D, okay? We need to figure out what D is in terms of A, okay? So I'm not going to go through the math to do that. It's pretty simple, but it's just trigonometry. What we get is that D equals A. Let me just check my notes. I don't want to misspeak. What we get is that D equals A over root 3, okay? So now if we plug that into our formula, D equals K. Q1 is that negative 1 coulomb charge. K times negative 1 over A over root 3 plus The next one's a positive 1 coulomb charge, K times positive 1 over A over root 3. And the next one's also a positive 1, plus K times positive 1 over A over root 3. Okay? So now this term and this term cancels out. We have that negative 1 and positive 1, so they minus each other. And this term is all that's left. So our answer is the potential at that point, V equals K times A over, K times root 3 over A. Okay. Now, calculating the electric field, I'm not going to go through because that involves some vector arithmetic, which we have not covered. However, for those of you who do calculate it, what I want you to do is not just brute force it completely and do it with the vectors. Notice the symmetry in this situation. Okay, so since this charge is the same distance away from this point as this charge, they both exert some electric field at points like that. Okay, but we add those contributions. And so actually, the horizontal components of those vectors cancel out, and we're left with only a vertical component, okay? It's like if I push my hands together like this, they're gonna go upwards, right? Like I'm gonna ultimately not be pushing one way or another, but if I keep pushing like that, I'm gonna be exerting a force that's upward. Or it's symmetry of the horizontal electric fields here. And then this charge adds a contribution that's also only in that direction. And so forget all the other components of the vectors. Only look at the component that points in this direction. Because you know just from symmetry of the situation that that's where the electric field has to point. Okay? That's problem 1, probably the least important problem of this problem set. So next up, we have this circuit right here. And I give you these values from the beginning. I tell you this voltage is 10 volts. This voltage is 5 volts. Okay? And these are just based on simulation values. And this voltage, it's at ground. So it's 0 volts. Okay? So, first of all, how much voltage does each resistor drop? It's a little trivial, but we'll still go through it. It's 5 volts here and 0 volts here. This is connected just by a wire to this point right here. So this point right here is also 0 volts. It's just all the same thing. It's all along the same wire. 5 minus 0 volts gives us 5 volts dropped on that resistor. There's also 5 volts dropped on this resistor, and there's also 5 volts dropped on this resistor for the same reason. Anywhere that's connected just by wire has the same voltage. Once we encounter the resistor, the voltage is no longer the same. But right there, the voltage is the same as 5 volts. Right there, the voltage is the same as 5 volts. And right there, the voltage is the same as 5 volts. They're all the same. We call it a node. Okay? Now, because, as we just established, the voltage here is also 5 volts, 10 minus 5 gives us 5 volts. Okay? So, 5 volts through resistor R4, 5 volts through R1, 5 volts through R2, 5 volts through R3. How much current flows through the resistor R4? Well, I've told you that 5 volts dropped by R4, and its resistance is 5 ohms. That symbol is the unit for resistance. It's the ohm. Okay? So if there's 5 volts dropped and it's a 5 ohm resistor, we know that V equals IR. V is voltage, I is current, R is resistance. So 5 volts equals I times 5. 5 equals 5I. And so current is 1 amp. Again, relatively simple question. Up next, how much power does the battery supply? Okay, so first of all, I just told you that the current through there is 1 amp, right? There's 1 amp of current that flows through there. And because the battery is directly connected to that resistor, it's the same current that flows through the battery. So 1 amp of current through the battery because the same current flows through this resistor, and that's one of our key assumptions, that along a single wire, which is what this is, the current can't change, okay? Even when there's resistors on that wire. The current can change, indeed it does, here, right? But not from here to there, because that's along the same loop, okay? So how much power does the battery supply? Well, it's a 10-volt battery with 1 amp of current. P, power, equals IV. Therefore, the battery supplies 10 watts. 10 times 1, 10 watts of power. Okay? So, yeah. Now, we know P equals IV, and we also know that V equals IR for a resistor. Okay? So, for this 5 ohm resistor, we know that the voltage drop is 5 volts, and we know that the current through it is 1 amp. Okay? So, there's a few ways that we can calculate the power. First, since we know the voltage drop is 5 volts and the current is 1 amp, we can equivalently say the voltage gain is negative 5 volts, right? The battery supplies positive voltage, the resistor gets rid of that positive voltage, and it has negative voltage gain, right? So negative 5 volts, because that's the voltage drop across that resistor, times 1 amp gives us negative 5 watts to that resistor, as in it dissipates 5 watts. The battery supplies 10 watts, the resistor dissipates 5 watts. Okay? However, we don't need to do that. If P equals IV and V equals IR, we can write P equals I times IR, or I squared R. Or, if we rearrange this to write I equals V over R, we can write P equals V squared over R. Okay? We know I is 1 amp. 1 amp squared is 1, times R is 5. 5 watts dissipated. We also know that V is 5. 5 times 5 is 25. Divided by 5 is 5. So through all of these different methods, we get the same thing. 5 watts of power through the resistor. However, we have to be careful with the signs. If I use P equals IV and I write V as negative 5 volts, I get negative 5 watts, right? Because V is indeed negative 5 volts as I go through that resistor, and it gets rid of 5 watts of power. However, with these formulas, the sign is not as obvious, right? And so we have to be careful, okay? Remember, the power through a resistor dissipates in the direction that, or rather, I should say, the positive direction is the direction that current is flowing, okay? You have to keep in mind what direction current is flowing when calculating with the power dissipated by a resistor or the power supplied by a battery. So how much current flows through each of the resistors R1, R2, and R3? Okay, so previously we said we drew a single wire, right? We had like a battery right here, we had a wire, and we had a resistor. Okay, and we said current going into this point on the wire has to be the same going out of this point, right? Just be like an arbitrary point right there, or right there, or right there, wherever. That always has to be true. But what if that point has a third connection? That still holds true. What goes in must come out. It's just now what goes in splits into two things that come out, okay? So if I were to zoom in on that junction, we have a current I1 going in, and then a current I2 coming out, and a current I3 coming out. This should be a very reasonable thing to expect. What goes in must come out. You can't just lose current to nothing, and you can't just gain current from nothing, right? So, yeah. So the total current that flows through all three of these resistors is still going to be 1 amp, okay? Because it's 1 amp of current that splits into eventually flowing there, there, and there from originally flowing from there. And these three recombine to come back down here. You can think of it like you're having a pizza, your teacher puts on a pizza party, and all the resistors came to the pizza party, and each resistor is divvying up the pizza. But these are hungry students. They're not going to leave any pizza left behind. It's like conservation of energy, now have conservation of pizza. Okay? They're not going to leave any of that 1 amp left behind. It's all going to go somewhere. And because the three resistances are equal, just by symmetry, by the fact that this is a so totally symmetric situation, we know the currents through each of them are also equal. Therefore, it's a third of an amp through there, 1/3 of an amp through there, and 1/3 of an amp through there. Okay? And now that we've done that, we've answered that question. And how much power does each resistor dissipate? To do that, we don't even need to look at the current, because we know the voltage drop and we know the resistance. So we just do 5 squared over 15. 25 over 15, that's 5/3 of a watt. Okay? And if we add up the total contribution, so the power through R1, so P total, so for R4, we calculated previously the power dissipated equals 5 watts. For R1, it's 5/3 plus 5/3. For R2, it's 5/3 plus 5/3 plus R3 is 5/3. 5/3 plus 5/3 plus 5/3 is 15/3, which is just 5. And 5 plus 5 is 10, which is the power supplied by the battery. So indeed, the numbers add up and this makes sense. Now the last part of this problem is a little involved. Next class, we're going to talk about series and parallel combinations of resistors. We are not talking about that this class, and so I explicitly say in this problem, do not use the rules of series and parallel resistors to solve it. Let's try to do this without that, okay? So suppose I tripled the value of R4 to 15 ohms. Okay, let me just redraw the circuit entirely with these new values. So 15, 60, 60, 60. I'm not writing the units, but these are all in ohms, okay? And then 10 volts. And then ground is here. Okay? So, first of all, I did not write 10 volts there and 5 volts there, because that's not necessarily true. Actually, it's not even true anymore, right? We're not resimulating the circuit. We're going to try to find those values ourselves by considering what's going on in this situation. Okay. So first of all, suppose the voltage here is Vx, okay? In the previous circuit, remember I mentioned, for any point that's connected to other points by a wire and nothing else, those points are all at the same voltage, right? So this point right here is at the same voltage as this point right here, which is at the same voltage as this point right here, which is at the same voltages right here and right here and right here and right here. However, it's not the same as right there, and it's not the same as right there because there's a resistor in the way, and that resistor drops or gains some voltage relative to that point. Okay? And the reason we use the term drop is because suppose the voltage right here was 10 volts, and the voltage right here was 0 volts, the battery gains 10 volts. But if I wrote 5 volts right there, then the voltage up here would be 15 volts. It's all relative. And so this resistor drops some voltage relative to Vx, okay? It's Vx minus whatever voltage is dropped by that resistor. So, first of all, we know Ohm's law, V equals IR. We can rewrite Ohm's law as I equals V over R. Okay? Let's say we know Vx. Let's call Vx just a variable that we're trying to solve for. Then the current flowing down here is just Vx over 60, right? Now, remember, we're assuming the voltage right here is 0 volts because we set that point to ground. So the voltage dropped by this resistor is Vx minus 0, which is Vx. So that's the V. The R is 60. And so that just directly, now we can get the current through that resistor, Vx over 60. That happens, same process here, because the voltage is Vx right there, the current going down is Vx over 60. Vx right here, so the current going down is Vx over 60. Now, we are also assuming that Vx is positive, which is why I'm drawing the arrow down like that. Okay? If it so happens that Vx is negative, that value will be negative, but this value will also be negative. And so the current will be going up, which makes sense. 0 volts goes to a negative voltage. Negative voltage is a lower potential than 0 volts, so of course 0 to negative makes sense. It's easier, however, to just assume it's positive and draw the arrows correctly given that it's positive. Vx goes to 0 if Vx is positive, so that's why we draw the arrow in this direction. Okay? So we have that. And let's set these back to what we know those numbers are. We know it's 10 volts right here, and 0 volts right there. So the voltage, what is the voltage dropped across this 15 ohm resistor? Well, if it's 10 volts before it and voltage Vx after it, the voltage dropped by that resistor is 10 minus Vx. Okay? So, again, this is getting just back to the same thing that we've been saying, that voltage drops are a really intuitive way to think about things. 10 minus Vx is the voltage drop of this resistor. So now we can get the current through that resistor, which is just 10 minus Vx divided by the resistance, which is 15. 10 minus Vx over 15. Okay? And that's the current that flows right here. Okay? So that current is 10 minus Vx over 15. Now remember, what goes into this node has to go out. Whatever's going in through here has to be equal to the sum of this, this, and this. Because there's nowhere else for the current to go. Okay? This is the teacher supplying the pizza, and this is the hungry students eating all that pizza. Okay? So that means we can just write that 10 minus Vx over 15 equals Vx over 60 plus Vx over 60 from this branch plus from this branch, Vx over 60. Again, what goes in must come out, okay? Now look, we have a bunch of numbers and one variable. Now it's just algebra, and we can solve for Vx. So I'm just going to write down the answer. You can do this if you want. We get, 40 minus 4Vx equals 3Vx. So 7Vx equals 40. So Vx equals 40 over 7. This is just algebra. If you struggle with the algebra, please let me know, and then I will, in future ones, I'll go through it more in depth. But solving this, you can just do that yourself. And so now we have the value of Vx. Vx equals 47 volts. Okay? And that's all we need. Because remember, what it asks for is the total power dissipated. From here, I can get the new voltage drop, which is 10 minus 40 over 7, and then do V squared over R for this resistor. I can also do the same thing for here, do 40 over 7 squared divided by 60. Same thing here, same thing here. I'm not going to calculate the numbers, but I think the point is good. This method that we just used, let's take a step back. The method that we just used is called the node voltage method. We took the voltage at the node and applied what's Kirchhoff's current law to solve it. This is a challenging question, and it is not at all expected that you should have gotten that yourself if you haven't seen this method before. But what I want to emphasize is that this method is really intuitive, and it's kind of a little obvious that it should work. So when we present node voltage actually in lecture and in lesson, hopefully it makes sense. So that is question 2. So, okay. Our next question is kind of reviewing what we've done already. Okay. So, first, we're going to draw an arrow next to each component that shows the direction that current flows in it. Okay. So, current goes up through the battery, right? 0 to 10 volts. So, it's going to be in that direction. And because we're in the same loop, it's going to be in that direction. And then since we have high potential here and low potential down there, it goes in that direction, that direction, that direction. Okay? Now, we then need to label that arrow with the value of the voltage gain or drop. So the voltage gain through here is plus 10 volts. And in the diagram, I give you that it's 10 volts right here and 5 volts right here. So 10 minus 5 gives, or 10 and 5 volts right there. So 10 minus 5 is 5 volts. So we get minus 5 volts, a voltage drop. Okay? 5 volts to 0 volts gives us minus 5 volts here, minus 5 volts here, and minus 5 volts there. Okay? So that's part of step 1. And step 2 is to add them all up. So 10 minus 5 is 5, minus 5 is 0, minus 5 is negative 5, minus another 5 is negative 10. So negative 10 volts is the total. And this is what we discussed in class. The voltage gains and drops do not necessarily need to add up to 0. The powers supplied and dissipated need to add up to 0. Okay, because power is about energy, voltage is just potential. It's not necessarily energy. So based on the voltage drop, what current flows through R3? Well, V equals IR. We know V, which is 5 volts. And we know R, which is 15 ohms. So 5 over 15 gives us a third of an amp. We did the same thing in the last problem. Through R4, 10 minus 5 is 5 volts. That's the voltage drop, right? 5 volts divided by 5 ohms gives us 1 amp. Okay? So add up all the power drops and gains. Okay? So to do that, remember that if I want to write the power, P equals IB, which equals I squared R, which equals V squared over R. Okay? Here, V squared is 25, R is 5. So that's 5 watts. Here, V squared over R is 25 over 15. So 5 plus 25 over 15. I'm just going to do that times 3, because that's the same for these 3 branches. That gives us 5 plus 5, which is 10 watts. And clearly, there's 10 watts supplied by that battery because we calculated there's 1 amp flowing through that resistor. We did the same thing in the previous problem. I cover it more in detail there. However, what I really want to cover in this problem is kind of the counterpart to nodal analysis, which is mesh analysis. Okay? Again, we're not going to use the actual method by name here, but I just want to build up an intuition for that method. Okay? So when we do this, we just assume for a second that I can draw individual loop currents. Let's call this current I1. Let's call this current I2. And let's call this current I3. Okay? So we have 3 loops and I've just given us 3 currents. And my hypothesis, let's just say, is that I can model the entire circuit where I have actual real currents flowing through each of these by just adding up I1, I2, and I3 and the behavior that each of those give. This gets into the fact that we're doing linear circuit analysis. There's a lot of really cool, deep math to explain why this actually works. It is intuitive why it works, but there are deep explanations for that as well. So, firstly, let's notice that in this loop, that current I1 is the only current that flows through this resistor. Through this resistor, the current that actually flows through it, so I1 is going this way, I2 is going this way, okay? So the current that actually flows in this direction, let's call that I. I is equal to I1 minus I2, okay? And this is the whole thing that mesh analysis is predicated on. Yes, there will be multiple different loop currents that flow through a given component in general, but I can just add them up. And as long as I keep track of the directions that things are going, I'm good to go, okay? So, similarly, let me get rid of that. So I1 is the only current that flows through the 5 ohm resistor. And as we calculated originally, the current that flows through this resistor is 1 amp. So we already know I1 equals 1 amp. Okay? The current that flows through this resistor, we also already calculated, is a third of an amp. Okay? So I3 equals 1 over 3 amps. And we are paying attention to the direction here. For example, if I drew this loop in the other direction, then this would be negative 1/3 amps. Okay? So now our goal is to calculate I2. So let's figure out what I2 is. We know that this current right here is I, and I is equal to I1 minus I2. Well, as we calculated before, we know that I is just equal to 1/3. So 1/3 equals I1, which is 1 amp, minus I2, which is what we don't know, minus I2. So add I2 to both sides, subtract a third from both sides, and you get I2 equals 2/3 of an amp. Oh, can you see that? Yes, you can. Okay. So I2 equals, is that reasonable? Is it reasonable to say I2 equals 2/3 of an amp? Let's check. First of all, this works. I1 is an amp. That's good. We know that there's a third of an amp flowing through here in reality. So 1 amp from I1 minus 2/3 of an amp from I2 gives us 1/3. Okay. Now we know the current going through here is also a third. So 2/3 from I2 minus 1/3 from I3 gives us 1/3 in that direction. So that's good. That's right. And finally, 1/3 is correct. So with these meshes, we've made sure that there's the correct current flowing through each of these resistors. And since the current is correct and the resistance is fixed, the voltage will also be correct. And as a result, we can then just solve the circuit. The circuit is solved, we can solve for whatever parameter we're interested in. This is called mesh analysis, and in general, we would not have these voltages originally, and we'd have to use a system of equations to solve for I1, I2, and I3. In the previous question, we used nodal analysis, which is, to me, a more powerful method, but both of these methods work in many scenarios, and they're both very powerful. And we'll discuss them in detail on Friday. This is just kind of an intuition for what's going on and why we're doing it and why it makes sense. All right, so this problem is a lot more qualitative than the previous problems, and the goal is kind of just to understand what a voltage drop is, what current is flowing, and just really solidify those relationships that we've discussed in the last class. So first question, easy question. Suppose I increase the resistance of R1. What happens to the total current flowing in the circuit? So you can think about this completely qualitatively, right? If I have a pipe that narrows down, I restrict the current. If I narrow it down even more, if I increase the resistance, I'm restricting the current even more. So less current flows, okay? And if I take that, let me say this. I don't want you guys to use series and parallel formulas yet. I want to first justify these formulas for you guys before you just use them. So that's not the purpose of this question. The purpose of this question is to say, suppose I wanted a device that measures the voltage, that measures the current. How do I construct this device? How do I use that device? Okay? So based on the fact that if I change the resistance of R1, or rather, change the resistance of anything in the circuit, I'm going to change the current that's flowing in the circuit. And so if I want to use a device that measures current, I need to not change the resistance. So this device that we add in, a good property it should have is that it shouldn't change the current of what we're measuring. It shouldn't change the current of what we're measuring. And to do that, it needs to not add any resistance or remove any resistance from the circuit. It needs to keep the resistance the exact same. Okay. And to measure the current, I probably want to put the device just in the way of it, right? So my ammeter, I'm going to symbolize it with an A. That's for amps is the unit of current, and A is for ammeter. And I'm going to have this device be put, we call it in series with these other components. This device has a resistance of 0 ohms, or something very, very close to 0 ohms. In lab, this is basically how it works. And what it does is it measures the current without messing with anything that's going on in the circuit. Now, what about if I wanted to measure the voltage? Voltage is a little more subtle, okay? Because on top of the fact that there's still some restrictions on what we can change and what we can't change, voltage is always measured with respect to a reference point. And ground in the circuit is not ground of my measuring device unless I connect them, okay? So, our voltmeter, it's going to have V, and it's going to have 2 prongs, okay? I need to attach those 2 prongs to something. So I'm going to put 1 prong to ground, okay? So that just tells the voltmeter what 0 volts is. It could, in principle, be attached to whatever my reference is, but the voltmeter is going to tell me the difference in voltage between those two points, okay? And so I'm going to attach the other point right there. Now, what property does this voltmeter need to have? Well, if I change the current flowing through this resistor, I change the amount of voltage that it's dropping, right? Because V equals IR, and R is fixed. So if I change I, I'm going to change V. But I don't want to change V. I need V to be fixed. So I can't change I, meaning that whatever current goes into here has to be the same current that goes into here. And 0 current, 0 amps, has to flow to that voltmeter. Otherwise, we're going to read the wrong voltage drop. And so, what property gives it the ability to have 0 amps? Infinite resistance, okay? So the R equals infinity ohms. Now, of course, it's not actually infinity. It's just a very, very large number, so much larger than that resistor. But think about what infinite resistance means, right? If I have a pipe with water flowing through it, and I constrict that pipe, I just close it off entirely, so tight that just nothing can get through. Infinite resistance has led to no current flow, right? So it's almost as if I've broken the circuit right there. Indeed, it'll be important to model infinite resistance as a break in the circuit. We call it an open circuit, and 0 resistance as just a wire. Because a wire is basically like a resistor with 0 resistance. You can think about it like that, right? And so if I have some current flowing through a wire, times R is 0, then V equals 0. No voltage is dropped through a wire. So it's just a qualitative question. Hopefully it helps you get a better sense of what resistance is, how we work with it in circuits, and how we think about it. So for this last problem, it's a circuit simulation problem. I'm not going to do it on here. If anyone has problems with circuit simulation, on Friday during that session, I'll be on Zoom and we can troubleshoot for you guys. But what I'm asking you to do here is draw a circuit that sends a 10-volt battery into a 100 ohm, I believe I wrote, 10 ohm resistor, sorry. 10 ohm resistor. So when you add the circuit, make sure to add a ground. LT Spice, I don't think it needs it depending on the circuit, but it's good to always add it. Add the battery and add the resistor. And if you're using false stat, I haven't used it before, but I'm sure the same things apply. Then go to simulate. So simulate's going to be at like the top of your screen. Press that. Go to configure analysis. Press DC op point, and then OK. And then you can just press run, that little play button, for any future simulations you want to do, and you've configured the analysis. It's just like a dot op on your circuit. That's what that's doing. So how much power does the battery supply? Well, we can just calculate this directly. We have 10 volts. We know those 10 volts have to be dropped by this resistor because there's nothing else to drop the voltage. So 10 volts divided by 10 ohms means 1 amp of current flows through the circuit, right? V equals IR. And so 1 amp times 10 volts, P equals IV. So 1 times 10 gives us 10 watts of power. And if you do the simulation, you'll see indeed that's true. Now, the next question is attach 4 more 10 ohm resistors in some funky combination. Maybe I can attach it like this, and then have it go like that, and then have another resistor right there. Just really make my life awful. Maybe I can do something like that. Now, this is not an easy circuit to analyze by any means. Indeed, this is not. Well, it is easy using some things that we'll learn in the future, but it's not immediately obvious how you've done what we've learned so far. So simulate it, see how much power it supplies, how much power each resistor dissipates. And then the third question, which you can do on paper, or you can just simulate, is kind of thinking about what leads to a lot of resistance and what leads to a little resistance. So there's basically 2 different ways I can attach resistors, in series and in parallel. Okay? What we noticed when we attach multiple resistors like this is we're adding their resistances. You may have seen this by the fact that the same current has to flow through all of them, and as we'll do next class, we'll derive what that means for how to simplify that circuit. But if we attach all these resistors in series like that, we increase the total resistance. We're having a more resistive circuit, right? It's the same thing if I have a spring, I put another spring in front of that spring, and another spring in front of that, or I should say, and another spring in front of that spring. That's a bad example, actually. It's a better example. If I'm holding apples. If I have one apple in my hand, if I have one apple in my hand, I put another apple in my hand, I put another apple in my hand. I'm increasing the amount of total weight that I have to hold, okay? That's what series resistance is. That's what series resistors are doing. They're increasing that load, right? So the other alternative is in parallel, okay? And what I mean by that is like this, like that, like that, okay? Now, what we notice here is that the voltage is the same all the way over there, and down here it's all 0 volts. So the voltage drop of these 5 resistors is all the same, okay? And since the voltage drop across all of them is the same, that can also help us derive a rule related to how we can redraw this as a single resistor with a new value. And as it turns out, and as maybe obvious even just looking at it, this decreases the total resistance of the circuit, right? Which kind of makes sense, because if I attach them all in series, then each one, if I do this, like I have a 10 volt battery like this, if I attach them like that, and this is a 10 volt battery, this one drops a little bit of the 10 volts, another little bit, another little bit, another little bit, another little bit, but all together, their drops have to add up to 10 volts because they're all in one loop. And if they don't add up to 10 volts, then that means I drop some voltage, I'm at like maybe 2 volts by the time I get to here. But I have to be at ground. I have to be at 0 volts. Okay. So here, each resistor drops only a portion of 2 volts, meaning that there's a lesser current flowing through them. Here, each resistor drops 10 volts, right? And so there's a greater current flowing through them, total. Okay? And so as it turns out, this is the configuration that requires the most power. Okay? What it comes out to be, I think, if you're using 10 ohm resistors, is it's 50 watts, I think. This is 50 watts. Whereas this configuration is 2 watts. So this is 50 watts, and this is 2 watts. That may be wrong. I'm just calculating it like in my head. That could be incorrect. But simulate it and see what you get, and just play with it a little bit. Get a bit of intuition for what's going on. That is the last question on this homework, so please feel free to email me with any questions that you have. And I hope this problem solves good. I think it's a really useful problem set for building your intuition.